Well, welcome everybody to Coffee with Caleffi. Delighted to have John Siegenthaler as our guest today, and he's got a lot to share and a lot to talk about. So, and we've got a great list of attendees here today. Thanks everybody for signing in. So, I'm gonna just do a couple intro slides here and talk a little bit. Siggy's gonna flip the slides as we go through this. A couple housekeeping slides, and then we'll get right to the presentation. So, yeah, this is just some tech support from GoToMeeting. If you have problems connecting or if your audio isn't good or something like that, that's a tech support number. Most of the time, if you just hang up and dial in again, or go out and boot back up again, it'll fix any problems. It's usually a connection problem. So at the end of the presentation, there'll be a little survey. If you want the slides that we're showing today, just check yes on that survey, and we'll get a PDF of the slides to you. And also the certificate of attendance will be mailed to you for one personal development hour. If you check the box and want that, we can, and obviously with your name and everything on it, so hopefully you can use those. And yeah, we're always like to toot our horn, and this is our angle mix valve and our tank mixer valve that we won the HR 2021 Grand Prize, the winner this year for Innovation Award on that angle mix. If you haven't tried that, try that. It's a really unique valve. I think you'll like that. Hydronics 28 is what we're going to be, is what's on the streets right now. And next issues, we're in work with issue number 29 already. Oh my gosh. And this is also a, what do you call, a virtual or digital edition available of the Hydronics going forward. A couple of the back ones I think we converted too. So you can get these mailed to you if you want the Hydronics. If you want the PDF of the slides, those are always on our website that you can download and put in your Dropbox or something. And now we've got the digital version of them that you can just kind of scroll through. So no excuse not to get the information from our Coffee with Caleffi. And yeah, this is coming up. Our next, in fact, our last for the summer. We're going to take a summer break here with the Shop Talk Showdown series. It's going to be Cody, my son Max, and Eric Ani. We're going to be talking about some of our favorite tools that we've used over the years. We got a great giveaway thanks to Rigid for that that press tool that you see up in the upper right hand corner. Is going to be a giveaway at the Shop Talk on Monday. And yeah, the next Coffee with Caleffi, that's my son Max will be doing it. This is a hot topic right now. There's, as you know, some cities, some states, and a lot of places are going to electric only or trying to go that way. So it makes for some interesting talk about how we're going to get there with the hydronics industry. So Max is going to take a look at some of that, what's going on, what the pros and cons of that are, and some of the equipment that's available. In fact, I was on the phone yesterday for a couple hours with a rep out in California that it's already happening out there in Berkeley and other places. Okay, how do we integrate solar and air to water heat pumps for hot water and stuff like that. So we're going to sort through that a little bit for you next month. And yeah, so always a pleasure, John, to have you on board. We got 90 minutes worth of content today, so grab a cup of coffee or something, get comfortable, and I think you'll learn a lot. And we've got a great sign up of contractors. So I think we hit a chord anytime we do a webinar on a topic like this, where we can show you, okay, this is what's going on out there, and if you stumble across one of these jobs, here's some options for fixing it. So take it away, John.
Well, thanks, Hot Rod, and folks, I'm glad to be with you this afternoon. I appreciate the audience size, and yeah, we're going to look at several things. The reference issue of hydronics that is close to many of the topics we're talking about today is number 19. So that's available at the Caleffi website. As Bob was saying, we could get that as a PDF, or some of you may have that as a hard copy. And we talk about proven hydronic systems, and in there we look at some what I call piping aberrations. These would be unproven hydronic systems, and we talk about what can go wrong and how to avoid that at a design stage, or how to correct that after it's been installed. So make sure you get a copy of it. Today, what we're going to be doing is, again, we're looking at what's wrong, how to avoid it if it's still at a design phase, or if you're a technician coming into a project and you spot an error, what are at least one way to correct it. And you'll find that in many cases, there are multiple solutions depending on hardware preferences and so forth. But we'll try to identify the most expedient correction. And then we'll finish up with what I call findings from the field. And I think you'll find some of these kind of interesting. So we're going to start off with one that I think the industry has pretty much digested at this point, incorrect circulator location relative to the expansion tank. So here we're looking at a very simple hydronic system. Let's say it's a simple series loop system, and you'll see the circulator is pumping into a boiler, and then coming out of the boiler, we've got an air separator, and attached to that, we have our expansion tank. So we could say we're pumping toward the expansion tank, okay? And we don't want to do that. And the reason for that, if we look over on the right, you'll see, I'll start with that blue line. Just imagine that as a horizontal piping circuit, and I made it horizontal so we don't have any difference in pressure based on elevation changes. All right, so just imagine maybe it's a circuit that goes around a slab on grade type building going through some baseboard, and then above it you'll see that red line that traces over the top of it. That represents a 5 pound per square inch static pressure in the piping circuit. So when the circulator is off, all those pressure gauges you'll see on the different corners of the diagram, they would all read 5 psi. That's just the static pressure in the system. Now, when we turn the circulator on, the circulator is going to produce a differential pressure. And in this case, it produces a 9 psi differential pressure between the inlet and the outlet. And the thing that's key to understanding this is that wherever the expansion tank connects to the circuit, in this case right here on the discharge side of the circulator, that's the point where the pressure does not change when we turn the circulator on, and it's called the point of no pressure change. So you see the green dashed line here. I want you to notice the green dashed line goes through the red line at that connection point for the expansion tank, but everywhere else in the circuit, the green line is either above in some cases or below the red line. That means there's been a change in pressure at that location because the circulator is running. So let's start from the point of no pressure change, and as we go around this circuit, we're going to go first to the left, we're going to make the corner and go back. If you look carefully, you'll see that green line is actually getting closer to the blue line, or I should say it's getting farther away from the red line. That's an indication the pressure is dropping around that circuit. And the pressure drop is the result of what's called head loss. That's mechanical energy that the circulator has imparted to the water. As that water travels down through that pipe, the turbulence in that water between the fluid molecules as well as between the molecules and the wall of the pipe, that creates a frictional effect, and that's called head loss, and the result is a drop in pressure. So as we go around way over on the far upper right hand corner, you'll see that the green line actually goes right through the blue line. We're at basically zero pressure at that point. And in theory, I caution you, you could drill a hole in the pipe and the water wouldn't go in or out only at that point. Now, if you keep following that green line as we go around, you'll see it's getting below the blue line. That means we're actually at negative pressure relative to the atmosphere. At this corner here, we're at -2 psi. And then finally, when we get to the inlet of the circulator, we're at -3 psi. We're 3 psi below atmospheric pressure. Any air vents or other devices that could potentially leak would be drawing air in to the circuit at that point. And the classic one is a float type air vent. It's basically there, it's going to act like a vacuum breaker. So we don't want this situation. If we're drawing air into the circuit, obviously we're going to get noise. And the other thing that can happen here is we can get into cavitation. All right. When we reduce the pressure on water, especially hot water, we're getting closer and closer to the vapor or the flash point of that water, where it changes from a liquid to a vapor, and that would cause what's called vapor cavitation inside the circulator. Now, unfortunately, a lot of this was not either understood, especially in the residential, light commercial sector of the market, for several decades. This schematic that you see over here, this was a common way to install a boiler with the circulator basically pumping into the boiler and towards the expansion tank. The commercial market understood this a little better, but for some reason that wasn't communicated downstream to the residential sector. And there were a lot of systems that had chronic air problems or chronic cavitation problems with the circulator as a result of this relative placement of the circulator compared to where the expansion tank is. So don't do that. The fix is to either move the circulator or move the expansion tank, and we want to pump away from the expansion tank. I'll give Dan Holohan a lot of credit. He wrote a book about this. He's talked a lot about it. The book is called Pumping Away, and I just put another little subtitle, Pumping Away from the Expansion Tank. It's not the boiler per se that is the most important thing. It's the location at which that expansion tank tees into the system. So here we are, we're pumping away. I always like to see 10 to 12 pipe diameters of straight pipe between whatever the last component is and the inlet to the circulator. That's just to stabilize it against turbulence, okay? And what that does now, I've made a couple changes in our diagram. For one, I've increased the static pressure. Increasing static pressure in a system, oftentimes that can correct a noisy circulator simply because we're elevating the pressure enough that we aren't causing either vapor cavitation or what's called gaseous cavitation. That's when we have dissolved air in the water, and if we get the pressure low enough, those bubbles will come out of solution and we get what's called gaseous cavitation. So here we've got higher static pressure, and you'll notice the expansion tank is now on the inlet side of the circulator. The circulator is still developing a 9 psi difference in pressure, from 9 psi here up to 18. And now that green line is elevated higher, and it's always under positive pressure. We're not going in any location where we're approaching either zero pressure or a negative pressure. And this is definitely the preferred arrangement between the circulator and the expansion tank. Now, I wanted to throw a couple other diagrams in. This is acceptable right here, all right, where the expansion tank is tapped into a header, and I'm stressing that this header is generously sized and it has very low pressure drop, and so does that heat source. If that's a cast iron boiler, there's very little pressure drop through it. So yes, you don't necessarily have to put the expansion tank into the bottom of the air separator. I know it's a common location and it would be fine, but this is another location. You'll tend to see this used more in European systems. And then if you're working with a ModCon boiler, here's another acceptable situation. Again, we can put the expansion tank several feet away from the inlet of the circulator if we have very low pressure drop. It's not about the physical distance per se between the expansion tank tap-in location and the inlet of the circulator. It's about the pressure drop over whatever that distance is. And by having generously sized headers, we minimize that pressure drop, and this would be acceptable. And this does keep the expansion tank a little bit cooler, and that's desirable because as we heat the shell of an expansion tank, that in itself causes the pressure to go up a bit. Okay. Now we're going to turn over to primary secondary piping, take a look at some common errors there. Here's one, and actually this relates to what we were just talking about. Here's a secondary circuit, and you see it's tied in with closely spaced T's down here, but the circulator is basically pumping towards the primary loop. And what happens in a situation like this is that because the expansion tank is teed into the primary loop, when it comes to the point of no pressure change, you can think of the primary loop as the point of no pressure change from the standpoint of a secondary circuit. So the secondary circuit essentially is seeing these T's as the point of no pressure drop, or no pressure change rather. So we don't want to suck the water around a secondary circuit. We want to push the water around a secondary circuit. Okay, so whenever you put a circulator into a secondary circuit, pump into the secondary circuit. All right, so here's the change. Okay, and you'll see there is, I do have a check valve in there on that. That could be one of the newer circulators with a built-in check valve. If you do this, make sure you purge that circuit out well. What you don't want to have is air getting trapped in the volute of the circulator. If that happens, the circulator cannot clear itself of air. And this, even though this check valve only needs about half a PSI of forward pressure to open, if you're essentially just churning air in the volute, that circulator will not clear that out. And there have been some cases where the circulator overheats because basically it can't cool itself. It doesn't know that there isn't flow going through it. It just keeps running, and that could eventually damage the circulator. So technically, I think it would be better to actually have the check valve up here, maybe a foot above the circulator. That would at least ensure that a rising column of water is going to displace the air out of the volute so that the circulator can, in a sense, grab the water and push it forward and push that air back out through the purging valve. Okay. Now here's another one, and I've experienced this in early days, a few decades ago, I guess I'd say at this point. How come there's heat migrating into this secondary circuit, even when the circulator's off? Well, it's actually pretty simple. Hot water wants to go up and cooler water wants to go down. So here we've got a column of warm water relative to a column of cool water over on the right side. Excuse me. The cooler water is slightly higher in density than the warm water, so it's heavier. So it's going to tend to perpetuate that flow, and you'll find that the heat will go a long ways. It might go all the way out through the heat emitters, and you might have a find where it's a nice late spring day like today, and you go up and happen to be maybe dusting, and you come near a baseboard and it's warm. How come the baseboard is warm when there's no call for heat? Well, it could be a situation like this with heat migration. And the solution to that is to put a check valve in, or to use a flow check valve. In the old days, a weighted plug flow check was common. Okay, so it's a buoyancy induced flow, and again, the solution is you could put a check valve in. It could be a check valve built in the circulator, or it could be Caleffi has some really nice check valves now. You could put one of those in, and that would solve it. Again, these check valves need about half a PSI of forward opening pressure. The circulator would easily produce that once it's running, but half a PSI is typically enough to prevent a buoyancy driven, what we call thermosiphoning flow through there. Okay. Now, I'll say some of the early days of primary secondary piping, one of the things that was being done was to install a ball valve between the T's, as you see down here. And the idea was we can close that ball valve and we could force a purging flow. If we have water being entering the system through the makeup system, with that valve closed, obviously we're going to force the water up around the secondary circuit, push the air ahead of it and push it back, and eventually out a purging valve at some point in the primary circuit. And that's understandable. The problem with this is, even with that valve open, you're creating more pressure drop between those two T's. And in theory, for ideal hydraulic separation, we would have zero pressure drop between the upstream T and the downstream T. Now, we can't get it to zero. Any real distance in there, even if it's 3 or 4 inches, is going to create some very small differential pressure, but we want to keep it as small as possible. So a better way to deal with this is not to install the ball valve in between the T's like that. is to put a purging valve on the return of the secondary circuit just before it hits the downstream T. And as you fill your system, you're going to first get the water into the primary loop. And if you connect a hose onto the side port of the purging valve here, close the inline ball valve, and simply keep water feeding into the system, it eventually has got to go up through here and push the air ahead of it and out through that purging valve. And the nice thing there too, that gives you isolation in combination with the isolation flanges on the circulator. We've got isolation on both sides of that secondary circuit. If we did have to service something in that circuit, it's easy to shut it off without affecting the water in the other parts of the circuit. So again, purging valve on a return as opposed to putting that ball valve in between. Now, when we do Coffee with Caleffi, we always get some questions, and one of the things that I wanted to do with this with today's session is actually show you some of these questions and then go ahead and answer them. So this is actually verbatim a question that came in. What happens in the system when tight T's are piped improperly, too far apart, not enough straight pipe between the T's, and so forth? So very similar to that situation we just looked at. So I want to show you some what I'd call undefined piping systems here, where I believe the intent was to create a primary secondary system, but as you'll see, it wasn't created. And here's one we've seen repeated numerous times, where the designer sets out a primary loop. So we've got this loop here, and I've put quotes around primary loop because really it is not a primary loop because of how those T's are placed in there. But conceptually, whoever designed this, or perhaps somebody just put components together to create this, the intent was to create primary, secondary, and I also believe an intent here was to put all three of the secondary circuits, the supply sides, near each other so they would all get the same water temperature. One of the downsides of a series primary secondary system is that there is a drop in water temperature as we go by any active secondary circuit, because we're taking heat out of that water, and the water has to drop in temperature when heat's removed from it. So somebody's thinking, if I just put all the supply sides together, I won't have a drop in water temperature, and then I'll bring all the returns together downstream. Okay, so the intent is good, but the problem we get into is we get differential pressures that are being set up, caused by the primary circulator, that are going to drive flow through these secondary circuits, even when let's say, for example, that the first secondary circuit is active, that circulator is on, but let's say that these two are off. Okay, and we've wired our controls so whenever any of these secondary circulators turn on, we're going to have the primary circulator operate as well. Well, what I want you to see is that with the primary circulator operating, let's say we could put a pressure gauge right here and we were to measure some pressure. I'll just pick a number. Let's say it's 10 PSI. Well, there's going to be flow down through this pipe because of this circulator being on. And when we have flow through a pipe, we have pressure drop. There's no way to avoid that. So the pressure is dropping, it's dropping, it's dropping, continues to drop and so forth. And let's say we get back to this point right here. Let's say that the pressure is now down to 8 PSI here. So we had 10 up here, and now we're down to 8. Well, let's say that the pressure right here, if it was 10 here and we've got a small length of pipe, maybe it's, I'll pick a number again, 9.5 PSI right here. 9.5 and 8. So we've imposed a 1.5 differential pressure on that secondary circuit, even when the circulator is off. And remember, these check valves only hold back about half of a PSI. So if we've inadvertently imposed a 1.5 PSI on the circuit, our check valve cannot hold that back. We are going to have flow in that circuit. We're probably going to have some flow over here, although it may not be quite as much because the pressure differential between that T and the return T would be a little bit less because of a smaller amount of piping in here. So The problem is going to show up as heat going into secondary circuits that are not operating. All right, that's going to be kind of the manifestation of piping it this way. All right, and again, this diagram just shows, again, between points A and B, we have a pressure drop due to that flow rate in the primary circuit. Okay, and again, I'll emphasize, I have seen this numerous times. I've seen it in residential projects. We've seen it in commercial projects. I've seen it on plans from consulting engineering offices. And again, I think the intent is to create a primary secondary system, but in a sense, trying to outthink how do I get around that temperature drop issue. By, and the solution, at least in concept, has been to put those T's close, put them all together on the supply side. Here's another one. This is quite similar. I've just moved the return T's a little bit. This is probably going to create less of a situation, but it's going to create another potential situation that you'll see here too. Again, the intent would be to line up all the supply sides of these secondary circuits so that they're getting essentially the same temperature, and then dump all the returns farther downstream on the loop. All right. So flow reversal is a potential problem that we're going to get here. And I want to show you what happens. Let's say that, and this is just a segment out of that last schematic. So let's say we've got a primary circulator here. We've got 15 gallons a minute going down through here. And I'm just putting some arbitrary flow rates. Let's say circuit number 1 is on, it's drawing 10 gallons per minute. Circuit number 2 is off, so I've grayed out that piping. And then circuit number 3 is on, it's drawing 4 gallons a minute. Well, whatever goes out has to come back through here. So we've got 10 plus 4, we've got 14 gallons a minute, plus, and of course, if we have 15 over here, we have to have 15 over here. So we have 14 coming back on the blue lines. That would imply this has to be 1 gallon per minute. No problem. As long as the primary flow is higher than the total of all those secondary circuits, this problem that I'm going to show you doesn't show itself. I'm not advocating doing the piping this way. I'm simply saying under those specific conditions, you won't see the problem. But change that so that the primary flow is less than the total of the secondary flow. So I've kept the secondary flow rates the same over here, 10, 0, and 4, but I've changed the primary down to 8 gallons a minute. Now again, whatever goes into a T has to come out of a T. So if we have 14 gallons a minute leaving, we have 14 gallons a minute coming back, we only have 8 that has to continue farther down the primary loop. So the only way that you take 8 away from 14 is you have 6 left over, and guess which way it's going? It's going this way. So we're actually taking 6 gallons a minute of cooler water now, depending on what the temperature drop through those circuits collectively has been. But we're mixing cooler water at 6 gallons per minute with 8 gallons a minute of hot water. And of course, we're going to get some kind of a blend depending on what those temperatures and flow rates are. And that is going to decrease the temperature going out to that first secondary circuit. Now, the flow rate is still 10 gallons a minute, but because we're getting a mixing effect, we're getting a lower supply temperature. We're not going to get as much heat output. And notice on circuit number 3, we got 6 gallons a minute coming back. This is only drawing 4 gallons a minute. This is 100% return water just being circulated out through the circuit. And there's literally 0 heat being added to it at that point. So again, I would tell you, avoid this piping. Don't look at this and say, as long as my primary flow rate is always higher than my total of the secondaries, I can avoid this. That is true, but it's not a good design approach. You'll end up just with a bigger pump and more power and bigger pipes, and it's not necessary to do that. Okay. So if you're going to do primary, secondary piping, the T's need to be as close together as possible. It's simply that fact. If somebody asks me, have I created primary, secondary piping? I say, do you have the sets of T's close together, as close together as you can get them? And if the answer is, well, I'm not quite sure, then it's probably one of those previous schematics we've looked at. So keeping the T's close together is essential. Remember, this is a form of hydraulic separation. And I'll be quite honest with you, I haven't designed a primary secondary system like this in a long time. And it's not because they can't work, it's because we have better methods of achieving hydraulic separation that don't create the temperature drop issue. For example, if this was 180-degree water here, and let's assume all 4 of these secondary circuits are operating, this might be 170, this might be 160, and we can do the math and figure out what these temperatures are. But if you could avoid this sequential temperature drop situation by redesigning the piping, you would, I would certainly encourage you to do that. So again, primary, secondary piping works. We've done it, but we've moved on to what I would consider a better method of hydraulic separation. Okay, and we'll revisit that a little later today too. Lack of differential pressure control. This is where we're dealing with zone valves. And just imagine we've got a system with, I'll start with a fixed speed circulator, a traditional circulator in there, and I'm just showing 4 zone valves. Well, what happens, we've sized that circulator so that we have enough flow under design load conditions. We're assuming all 4 of those zones are operating. We have enough flow going through there, and there's a certain differential pressure established across that circulator at that flow rate. Now, think about what happens when we close a zone down. What happens is we're going to have less flow through the circulator. And if you think back to what a pump curve does, when we go to the left, when we decrease the flow rate through a circulator, we get an increase in differential pressure, which means that the zone circuits that remain open feel more of a push, and the flow rate will increase in those circuits. If we close another zone valve down, that problem just keeps coming. And this kind of illustrates it. This lower blue curve would represent the system curve when all 4 zone valves are open. And think of it as a 4-lane highway. All 4 lanes are open. We have the least amount of flow resistance in our distribution system. And the red curve is the pump curve for this fixed speed circulator. So where the system curve and the pump curve cross under the condition where all 4 zones are open, we have a certain flow rate and a certain differential pressure. Now, as we close these zone valves down, this operating point is going to shift up and to the left. You can almost think of these blue curves as just getting steeper and steeper as the zone valves continue to close down. And if we got down to the point where we only had 1 of these zone valves open, the system curve would be quite steep, and you can see we've picked up a lot of gain here in differential pressure. And that pressure is, that gain in differential pressure is going to be felt across the zone that is still open. And you can get situations like flow noise. You could even, under extreme conditions, you can get erosion, especially in copper fittings, elbows, and so forth. I've actually gone into mechanical rooms and heard these high-pitched whining sounds coming out of zone valves because you've got 15 zone valves in a commercial size fixed speed pump, and 1 zone is open, and the flow is just screaming through that valve, literally. So we need a way to deal with this, okay? And the classic solution for a long time, and this can still work for you today, is to install a differential pressure bypass valve out here on the end of the headers. And what this does is it remains fully closed under design flow. So under design flow, we have the exact same system curve and the pump curve. We have the same flow rate that we had before. But as we start to close zone valves down, you see we get up to this point, and this is called the threshold pressure of the differential bypass valve. And of course, you can set that by adjusting the knob here. And I typically suggest setting it for anywhere from 0.5 to 1 psi above the differential pressure that you would have across the circulator when all 4 zones are open. We don't want the differential pressure valve active under design load conditions. We want all the flow going out to the zones. But as we start to close zones down, you'll see when we start to reach that threshold pressure, what happens in effect is that it's as if the upper portion of the pump curve got truncated or changed from this dashed thin red line into this solid red line, okay? And you'll see it's going up slightly as it goes to the left, but nowhere's nearly as much as the dashed line is increasing. So we get a relatively small change in differential pressure, which is generally acceptable. Now, this was the solution when we were basically limited to fixed speed circulators. Today, what I would consider a better solution is a variable speed pressure regulated circulator. And in this case, it would be set for constant differential pressure. And what that does is as our system curve goes up, the pump will automatically feel an attempt to go up in differential pressure. But just like a cruise control can feel an attempt for your car to change speed, then it corrects for that. It feels what's called in a control sense an error. And an error simply means a deviation from some target value that we're trying to maintain. And it provides a corrective action. In this case, as the zone valve closes, it's going to bring the speed of the motor on the circulator down, and that's going to shift this pump curve down. And the net effect is that that operating point is just going to move back to the left. It's not going to go up or down vertically, which means we're maintaining the same differential pressure across the zone valves that remain open. And as we continue to close more of those zone valves down, this point just keeps shifting. And finally, when we have just one zone open, you can see we're at the same differential pressure that we were at when all 4 were open. And I like this because, you don't need the differential bypass valve. And the other thing is that the energy savings associated with this, as the pump reduces speed, obviously the power input to the motor goes down. So over the course of a season, this can result in a pretty substantial electrical power savings, in addition to what you get with just the fact that you're using an electronically commutated motor versus a standard AC motor. So today, this has pretty much become the standard. As variable speed pumps were first introduced, and this is probably rolling back now at least 15 plus years, they were quite expensive when they first came over relative to fixed speed circulators, like maybe 3 to 4 times as expensive. And they were limited at that point, but that price point has come down substantially to the point where now if you're doing valve-based zoning, either with electric zone valves or perhaps thermostatic radiator valves or even manifold valve actuators, any type of valve-based zoning, combining that with a variable speed circulator is I would consider state-of-the-art practice today. Okay, now here's another question that came in. Can you line size modulating zone control valves? And I put the word zone in here in gray because that wasn't a literal quote. Or I'm sorry, the word zone valve was, but I'll show you. And I thought this was interesting. I know the answer, but junior colleagues that may attend may not. So let's look at that, okay? And I'm changing it over to restrictive mixing valves now, okay? But we're still talking about line sizing. And what that means is if we have a 1-inch pipe, we pick a 1-inch valve. You know, that's what line sizing means. It doesn't mean we look at the flow coefficient of the valve. We just size the valve for whatever the pipe is. Here's a good example of that. This is actually a highway garage in upstate New York, and you'll see there's a radiant manifold here with 8 circuits on it. And if you follow it back through, here's a circulator. And take a look at that right there. That is a small thermostatic mixing valve that was really intended for a domestic water application. And that's going to have a flow coefficient of perhaps 2.5 to 3. And if you've not heard of flow coefficients. What a flow coefficient is, or a CV value, it's the number of gallons per minute through the valve when it's fully open that will produce a 1 psi pressure drop. Okay, so for a mixing valve that has a CV of 3, if the valve is fully open, passing hot water or whatever warm water is coming into the hot port directly out, at 3 gallons a minute, it'll have a 1 psi pressure drop. Now, what does that mean? Well, let's increase it from 2.5 gallons a minute up to 8 gallons a minute. We got 8 circuits here. Let's say we're trying to get 1 GPM per circuit. Well, to do that, just to push that flow 8 gallons a minute through that valve, and by the that has a CV of 2.5, we would need over 10 psi. And I want to stress, that's just to push it through the valve. That's not to push it through the floor circuits or that copper tubing or any fittings that are in that circuit. And it gets even worse. If we were trying to get 12 gallons per minute, let's say we wanted 1.5 GPM per circuit, just to push the water through the valve, we would need 23 psi. And obviously, we're not going to get anywhere close to that differential pressure. So what happens? Well, what happens is you don't get enough flow in your floor circuits. The classic symptom is a high temperature drop. If you go into a project like this, read the thermometers that are on the manifold, or just, put your hands on the supply pipe, you feel a certain temperature, put your hand on a return, and it's 30 or 40 degrees lower than the supply temperature. That's a good indication that you have a flow starvation condition. And now start looking back, what is causing the bottleneck in that flow? And again, we see these valves being used. I'm not against these if it's a very small manifold, maybe 3 or 4 circuits in a basement, you get away with that, okay? Because you're only dealing with low flow rates, maybe 3 gallons per minute. But if you're looking for 1 GPM per circuit and you put a 10 circuit manifold on one of these, you're not going to get anywhere near 1 GPM per circuit. And of course, that ultimately means you're not getting enough heat output. So I want to stress, these small circulators, even at their maximum differential pressure point, which would be at 0 flow, something like this, a little 80-watt circulator is probably only producing 4 or 5 psi. That's it, and that's to drive the flow through the mixing valve as well as the floor circuits. So generally speaking, I'm not a fan of using thermostatic mixing valves unless they have high CVs. And there are some valves on the market that do have high CV values that can be used for these applications. But my experience has been generally a motorized mixing valve, especially in a commercial application, is probably going to be less expensive and actually more versatile than these. If you're looking to do control actions like outdoor reset control, you really can't do that with a thermostatic mixing valve. So be careful of flow bottlenecks, okay? And I put that red rectangle there. I don't know what that is at the end. If you look back again, you can see here, somebody's connected across these 2 pipes as if they're headers, and yet out here at the end, what it looks like is there's a couple T's and it just does a U-turn. So this is probably a combination of that previous schematic we looked at and the added burden of a very flow restrictive mixing valve here. And Caleffi does have some nice mixing stations. You can use 3-way valves or 4-way valves, and these can be motorized or they can be thermostatic. And these make sure that you've got enough CV, a high enough CV value that you're not creating that flow restrictive condition. And of course, another option, I threw this in just again, show different solutions, would be to use a variable speed injection circulator as opposed to a mixing valve. A lot of these out there at this point, they work well. Again, we don't have a flow restrictive situation. So I'm showing it simply as an alternative to either a 3-way or a 4-way mixing valve. Okay, lack of hydraulic separation. What is hydraulic separation? Anytime we have 2 or more circulators in a hydronic system, and they can be operating at the same time, which is often, almost always the case, I should say. We want those two circuits to operate as if there's nothing else in the system. When we have two circuits, we want them to be completely unaware of the presence of each other. Okay, so to really define that, I want to show you what we call common piping. So here's a very simple piping circuit. We've got two circuits in here, two circulators, and you'll see that where these two circuits come together, this little red cloud, I've called that the common piping. Now, that could be a number of things. It could be a tank, it could simply be a length of pipe, or it could be a long length of pipe, fittings, valves, you know, whatever. But the pressure drop in that common piping is going to determine whether these two circuits are hydraulically separated from each other. And the basic idea is we want that pressure drop to be as low as possible, okay? Keep the pressure drop in the common piping as low as possible, and that will get you hydraulic separation. So now I'm just replacing that little red cloud with another component. Now you could look at this and say, well, that looks like a buffer tank, and it might be a buffer tank. It might be a hydraulic separator. It, you know, anything that has a large cross section, you're going to have very low flow velocity in that portion of the circuit. And low flow velocity means you have very low, what's called dynamic pressure drop, very little change in pressure due to flow. So now we do have hydraulic separation between those circulators, all right? And just to show you what happens, sometimes, you know, people want to look at hydraulic separation. Well, what's actually happening here with pump curves and system curves and so forth? So let's start out with circulator number 1 is operating, but circulator number 2 is off. So here's circulator 1, that's running, circulator number 2 is off. And the blue curve over here, this blue curve represents that system head loss curve. So that would be the system head loss curve around circuit number 1, including through here. And this is very, very small pressure drop, all right? Now, the next step is to look over here. The pump curve and the system curve intersect, and that becomes the operating point. And if we were to draw a line down, we could read some flow rate. I don't have numbers on this scale, but again, I'll pick a number. Let's say it's 10 gallons a minute, right? Now we're going to turn on circulator number 2, and we're going to leave circulator number 1 on. So both circulators are running, okay? So what's going to happen is we're going to have increased flow rate across this common piping because we have flow in both circuits now. However, because we've specifically made that common piping to have very low pressure drop, that change in differential pressure due to the higher flow rate is very small. So what happens is circulator number 1, in a sense, feels the green curve now instead of the blue curve. And you can see the green curve has shifted up very slightly from the blue curve, but the effect is very, very small here. The change in flow rate in circuit number 1, when we turned on circuit number 2, is very small. Maybe we jumped from 10 GPM down to 9.9 GPM. And that's not going to have any detectable negative effect on the performance of that circuit. So while we could argue that we don't have perfect hydraulic separation, perfect would mean, you know, when circuit number 2 turned on, circuit number 1 stayed at exactly 10 gallons a minute. No, it didn't. It went to 9.9. From a practical standpoint, we have very adequate hydraulic separation, okay? Now, let me show you. Let's make the situation bad, all right? And the way we make the situation bad is we take out a common piping segment that had very low flow resistance, and we replace it with something that has much higher flow resistance. So that zigzag you see here could represent any combination of components that collectively creates a relatively high flow resistance. This is taking us in the absolute wrong direction if we're trying to achieve hydraulic separation, okay? And here's an example. Some of you may remember a boiler called the Glowcore, which was on the market, gosh, many years ago. I want to say probably 25 plus years ago. And it was one of the first condensing boilers in the North American market. And thermally, it performed well, but it had a very compact and a very high pressure drop heat exchanger. And being, in a sense, very new technology, installers were taking this Glowcore boiler and they were installing it just like they would install a cast iron boiler. In fact, maybe they were replacing a cast iron boiler that has very, very low flow resistance with this Glowcore boiler. And all of a sudden, problems started to show up, flow-related problems when we had zone circulators. And again, think of this high flow resistance boiler as that little zigzag on that schematic. We have to push all the flow collectively from all the active zones have to go through that boiler. And if that creates a high pressure drop, that is going to start interfering with hydraulic separation between those circulators. And this was a significant problem as these high flow resistance boilers started to come into the market. And before the collective trade, and I by that I mean everything from manufacturers through installers, engineers, you name it, they just didn't understand what was happening. Eventually they figured it out. That was the good news, okay? But the problems here were basically reduced flow rates in zones and inadequate heat delivery. So how do you fix it? Well, today we know just about all ModCon boilers that have any significant flow resistance, we're going to interface them with either a pair of closely spaced T's, or as you'll see in another schematic, with a hydraulic separator. So what we're doing is we're removing that high flow resistance and we're putting in a dedicated circulator just to move the flow through the boiler. And then again, hydraulic separation here at the closely spaced T's. And I do want to stress short, generously sized headers. Keep the headers as short as you can. And a good sizing criteria that I promote would be figure out what your total flow is when all these pumps that could operate simultaneously are on, and then size your pipe for about 2 feet per second flow velocity. By keeping the pressure drop through the headers very small, we're basically working in concert with this hydraulic separation concept right here. All right. Now, here's another question. Does John see value in using a combination hydraulic separator, air eliminator, dirt separator products? And the answer is yes, I do see value in that. And there's a good example of it. That's basically 90% the same schematic we just looked at. I'm replacing the closely spaced T's as well as an air separator. I'm replacing it with a hydraulic separator. And this is actually doing 4 things for me. It's providing the hydraulic separation between the boiler circulator and our zone circulators. It would have a coalescing media up here, so we're doing air separation. So we don't need a separate air eliminating device, air separator in the system. And down at the bottom here, we're getting both standard dirt separation, and with the magnet here, we're getting iron oxide or ferrous metal particle separation. And that latter function is very important with new circulators that have the permanent magnet motors in them. So this, again, in my opinion, is the way to go today, because yeah, you can duplicate the functionality with closely spaced T's and a separate air separator and a separate dirt separator and so forth. But by the time you pipe all that together, you'll need a lot more space in the mechanical room, and you'll probably be at a higher cost than simply using a combined function device, a multifunctional device like a hydraulic separator. How about this one? Unnecessary reverse return piping. And I want to show you an example of this. This is where we're doing multiple boilers, and this could be, I'm showing conventional boilers here, but it could also apply to modulating condensing boilers. We've got reverse return. So we've got separate circulators on each boiler, and you can see the first boiler that goes to the hydraulic separator here is actually the last boiler on the the feed line or the lower temperature pipe coming out of the separator. Now, this will work, but pipe's expensive, and especially today. So if we don't need it, why do we want to purposely throw more pipe in there? So what I would tell you instead is to simply go with short, generously sized headers and a direct return system right over to the hydraulic separator. Now you could say, well, won't the flow rate through the boiler that's out here be lower than the flow rate through this boiler? And the answer is yes, it will be. But it's a question of how much lower, and does that slightly lower flow rate in the farthest boiler away from the hydraulic separator, does it have any negative effect on the operation of the system? And the answer is no. If we have a delta T of, let's say, 20 degrees on this boiler and it was maybe 20.2 degrees on this boiler, that's really of no consequential effect. And keep in mind, all this flow from the boilers gets combined over at the hydraulic separator anyway. So it's simply, today I would tell you, keep the headers short, generously sized, and eliminate the reverse return. Reverse return works when we have a single circulator going through multiple parallel branches, and we're trying to get close to the same flow rate in each branch. That's a plausible case for reverse return. That's not what we have here. We have multiple circulators, not a single circulator. Okay. And we could put some balancing valves in here if we want to have exactly the same flow rate. Certainly we could throw in some quick setter type valves and we could adjust that. Okay. And that would also function as an isolation valve for you. Okay. Another question: best way to prevent flue gas condensation on non-condensing boilers. Actually, I don't like the term non-condensing boilers. I know what they mean. They mean a boiler that isn't intended to operate with condensing conditions, but any boiler, given the right conditions, will operate with condensation. Anyway, best way to prevent flue gas condensation on non-condensing boilers and low temperature application with a design temperature 100 to 130. Well, let's look at what happens, lack of boiler protection, okay? What I call a conventional boiler simply means a boiler not intended to operate with sustained flue gas condensation. And these are just some examples of what can happen. You're going to get condensation in the flue, if not in the boiler. This vent connector over here on the left is only about 6 months old, and you can see that galvanized pipe has been completely corroded right through by, this was actually on an oil-fired boiler, probably pretty low sulfur oil. So we had plenty of sulfuric acid going up in that flue, condensing with the water vapor and coming down and just eating a hole through that. This is another one. This is back probably again with 500 part per million higher sulfur fuel oil. It was actually where the the vent connector was crimped and pushed up into that chimney. So what was happening here is that the flue gases were condensing in the chimney and then running down and then running on the outside of that pipe and making quite a mess. And here's a copper tube heat exchanger from a boiler that's completely caked up due to low temperature operation. So we've got to avoid this, okay? And there's two things that we have to avoid flue gas condensation. We must be able to sense and react to the boiler inlet temperature. And we have to have a way of thermally disconnecting the heat source from the load, all right? And I call this this is a classic way to look at any mixing. We have a boiler loop and a distribution loop, and we have what's called a mixing assembly in between. And this could be a lot of different hardware configurations. It could be 3-way valves, 4-way valves, it could be injection, but you'll notice that that mixing assembly is a bridge between the boiler loop and the distribution system. And just imagine if we have the ability to close that bridge, no BTUs can leave the boiler loop and get over into the distribution system. We have the ability to completely disconnect the heat source, or the heat source loop, I should say, from the distribution system. And that is this so-called thermal clutch, just like a clutch in your truck. If you push that pedal all the way down, You've disconnected the engine from the drivetrain. Okay. Another misconception about boiler protection is that somehow it limits how fast heat can go to the building. And that's not true. If you're doing boiler protection the way we're going to talk about it, the boiler will be running nonstop. If you're heating up a cold slab, maybe it's a commercial garage type facility, that boiler could run hour after hour, and it should not be shutting off. And it simply means it's producing all the heat that it can, and all that heat is going to the distribution assembly, even though we're protecting the boiler in the process. Now, here's an example. Here's a three-way motorized mixing valve, and you'll notice there is no boiler inlet temperature sensor. And what's happening here is that the boiler is putting out 50,000 BTUs per hour, running continuously, and that distribution system over here on the right is dissipating 50,000 BTUs per hour. We have thermal equilibrium, okay, between the rate of heat production and the rate of heat dissipation. And I did some calculations over here, and with the circuits that we're assuming here, 6 circuits, 300 feet long, 12-inch spacing in a bare slab, this water temperature only has to get up to 111.4 degrees. There's no reason for it to go any higher. All right, it's putting out all the heat. The floor is putting out all the heat that the boiler can put out. And if you look at what's happening on our return water is at 93 degrees, and it's simply going to go right back into the boiler, and we're well below typical dew point of about 130 degrees for a gas-fired boiler. So our boiler's operating down here between 93 and 111, and we're below dew point. So you can see we're going to operate that boiler hour after hour with sustained flue gas condensation. It's going to destroy the boiler. It's going to destroy the vent connector, and the worst case scenario, it's going to allow carbon monoxide to go into that building, and you don't want to go there. Now, here's where I've simply added a bypass circulator. And the thinking is, okay, I'll make sure we have warm water blended into that 93-degree cool water before it goes back to the boiler. Well, what's lacking here is the temperature sensing on the boiler inlet. Okay, and you can see we've boosted that boiler inlet up a little bit. It's gone from 93 up to 106, all right? But the distribution system here, still the supply temperature remains at 111.4. It doesn't go any higher. And I put in here, let's say somebody set the mixing controller for 125. It doesn't matter. It won't go there. It doesn't have to, because it's putting out, again, it's dissipating all the heat the boiler can produce at 111.4 degrees supply temperature. So just putting in a bypass circulator by itself without that boiler inlet temperature sensing is not going to assure the boiler is protected. And again, you can see here's where the boiler's operating between 106 and 111 and well below the dew point. So we have sustained flue gas condensation. All right, so finally, let me just jump to, here's the fix. All right, now we've got boiler inlet temperature sensing. And this, the controller that's driving this mixing valve is continuously looking at this sensor, and it's trying to keep that at or above 130 degrees. And some of these mixing valves, and most of them, you can set that, but 130 is a common setting for boiler protection. So it's going to give priority to getting that temperature up to 130 over priority to get, control the supply temperature out here. Essentially, this is going to give you both. It's giving you 50,000 BTUs per hour of heat transfer from the boiler to the load. So we're taking all the heat our boiler is capable of producing, sending it to the load, and we're maintaining the boiler inlet temperature above our dew point. All right, so we need to have that boiler inlet temperature sensor in there. A bypass pump by itself will not do it. Okay. Here's another example. Here's a three-way mixing valve. You'll see there's nothing here that can boost the boiler inlet temperature. We're not measuring the boiler inlet temperature and reacting to it. So again, we're going to condense our boiler. All right. There's no thermal clutch between the boiler loop and the distribution loop here. Now, here's a thermal protect valve. This is a high flow coefficient thermostatic valve that Caleffi has. It's primarily designed for a biomass wood boiler type application, but there's certainly nothing that limits its use to that. That can be used, and this is going to give us our temperature sensing on the boiler. It's not sensing it here, it's sensing it inside the valve, and it's going to blend hot water in as necessary to keep that boiler inlet temperature at whatever that valve is set for. And this particular valve does not have a knob on it. Basically, the cartridge that goes into that valve, when you order that valve, you'd order it with a specific cartridge for a certain return temperature. And the other valve out here, this is controlling our supply temperature. Okay, here's a three-way motorized valve. Again, we've got to create a secondary mixing point to boost that boiler inlet temperature. By using closely spaced tees, we do have hydraulic separation between the boiler circulator and the distribution circulator, but I really want to stress we are sensing and reacting to the boiler inlet temperature. We do have a thermal clutch because when necessary, this valve will completely close the hot port. If no hot water gets in, no cold water goes back, and this boiler loop is just recirculating, okay? And it'll quickly come up above the dew point temperature. We can also do it with a four-way motorized mixing valve. I'll just point out Hydronic's number 7, if you're interested in mixing, where we look at all different types of mixing options from injection mixing, three-way valves, four-way valves, and so forth. You can get a lot of more detailed information on mixing in Hydronic's number 7. Here's one. We've done a fair amount of work with these pellet boilers, and we'd see a situation where somebody's using a variable speed pump that has temperature sensing capability, and they're setting it up like this. And the idea is if this temperature gets below dew point, we're going to speed this up, and thinking that we have hot water available up here that we can push down and mix with the cool water. Well, again, if you look at this, the two things that we stress for fundamentals, we are measuring the boiler inlet temperature, so we can check that box. What we don't have here is a way to completely disconnect the boiler from the load. In this case, the load is this large thermal storage tank that could have 500 gallons of room temperature water in it. So this is not going to work. No matter how fast that bypass pump pushes the flow, we're still going to be at a sub dew point operating temperature, and we're going to have flue gas condensation inside the boiler. But the good news is, with a simple rearrangement of the piping, we can fix that. I'll just jump to that. That's not it. Here it is. We're just moving the variable speed pump now so that it connects the boiler loop over to that thermal storage tank. And that variable speed pump is our clutch. If that pump is off and we have closely spaced tees here, this boiler loop is just going to recirculate. And that will allow that temperature to come up very quickly, which is going to happen as the boiler goes from a cold start and starts to warm up. Basically, you just have flow here. This pump will be off. And then once we get up to 130 or whatever it's set for, this pump will start to ramp up in speed and start to pull BTUs away from the boiler loop and send them off to the load, and of course send cool water back. If it gets going a little too fast and this temperature starts to drop, this pump's going to slow down. So yeah, you can use a temperature set point circulator, a variable speed circulator, for boiler protection. It's a great application. Just put the pump in the right location. Make sure that you've got the thermal clutch. Okay. Again, here's one that doesn't work. We don't have complete separation. All right. We don't have the ability to completely separate it. We're sensing boiler inlet temperature, but we don't have a way to completely isolate the load from the heat source. And I'm going to move kind of fast, just looking at time that we've got here. Again, I encourage you to download that PDF and take a good look. I try to put enough text in the slides here so that when you go back and look at it, you can see what's going on. Okay, this one, the intent, 2 areas of floor heating at 2 different mixed temperatures. So the installers put a couple mixing valves in here so they can set them at different temperatures. The fault here is that do you see anything that's going to be a problem? Now, the problem is you're going to get very, very little flow through those manifolds. And it has to do with where the circulator is located, all right? We don't have a circulator between the load and the mixing valve. And anytime you have a mixing valve and a load, you have to have the circulator in between. It could be on the supply or it could be on the return, but not down here, okay? What's going to happen, remember, as it says over here, when flow leaves the circulator, it only cares about getting back to the return side of that circulator. So flow that would go up through here would work its way through the porting in this valve, come over here, and simply come back through the boiler, okay? We actually saw a job like this where there were 7 of these thermostatic mixing valves installed, pretty much just like you see here. And they were getting a tiny trickle of flow out through the heat emitters, but it was well below what was necessary. So now we've moved the circulators. Okay, we've got circulators between the load and the mixing valves. And notice too, I've also put in a hydraulic separator. So we're picking up air, dirt elimination, as well as hydraulic separation between these circulators and the boiler circulator. And then I'm not sure if you noticed in the previous slide, there was flue gas condensation. Because we've got a thermal protect valve in here now, we're able to keep the boiler inlet up above that dew point temperature. So this would be one of the ways you could correct that previous situation. Okay, 2 independent zones of radiant. This shows it with motorized mixing valves. Okay, that was the difference. Notice again, the circulators between the mixing device and the load. And again, we've got the 3-way thermostatic, the high CV thermal protect valve in there to boost our boiler inlet temperature. Okay, so let's say out here we're getting possible flow reversal. We've got a zone that's off and a zone that's on. So let's follow the flow here. We're going up through the mixing valve, coming back down through here. Now we'd like to think that the flow is smart enough that it knows it's all supposed to go back through here. But let's follow another path. All right, we're coming up. Notice there's no check valve here. And let's say this motorized mixing valve shut off where there's some ability for flow to pass between this port of the valve here on the right and this lower port. Remember, that's just a segmented cylinder that rotates with the motor. And when you remove power from it, it just stops at whatever location it was at. So this is another potential path for that return water to go. And of course, it's going to come back over here. It's going to blend in, and within limits, this mixing valve should be able to compensate for that. But this effect over here is undesirable. And to stop that, what we're going to do is throw a check valve in. And notice the check valve has to be between the cool port that goes into the mixing valve and where that circuit connects back to the header. Okay, the check valve up here is not going to help us. We need the check valve down here. So we could put a couple check valves in, one on each side. That would eliminate any potential. So anytime we're working with a 3-way mixing valve like this, where we have multiple zone circuits coming off of headers, I always look for that check valve to be in there. And actually, you could put that right next to this purging valve down here too. Again, the hydraulic separator and the thermal protect valve to boost that boiler inlet temperature. Okay, so we've been looking at a lot of schematics. I want to show you some photographs, and I call these findings from the field. Okay, and another way to look at this is what's wrong with this picture. Okay, if you like to cut firewood, that's not a good idea right there. So here's a photo, and I'll let you look at that. Think about it a little bit. Look it over. Do you see anything that's wrong there? With face-to-face training, you know, we could people would be yelling out answers here, but let's just kind of go down through there. First thing I see is circulators, wet rotor circulators with vertical motor shafts. That's really not how those circulators are intended to be installed. Horizontal shafts on your circulators. And we see this. I've seen some otherwise beautiful installations where just out of convenience, the installer put the circulator with a vertical shaft. Now, I won't say that the circulator will not run at all, but remember those bushings that are no circulators are not designed for the type of loads that you can get when you have a vertical motor shaft like this. So it likely could lead to premature failure of the circulator. You could get air trapped up in the can of the circulator. What else? Well, whoever did the piping insulation here took the easy route. They did the straight segments first. They've got some challenging sections to complete that insulation. Water valves and connections located above electrical components. That's one of the things I actually talking to an installer this morning about it. You see, we've got a lot of expensive controls here, and up above it, here's a manifold, and actually there's another one right over here. Now, there's a good chance those manifolds won't leak, but there's also a possibility that they will. And if they do, you can see where that water is going to go. It's going to drip right on top of those controllers. So if you've got to shoehorn the controllers in, put some kind of a little metal protective, shed over the top of them or something. Preferably, I'd like to move the controllers off to the side and have what I'll call a control center and bring the wires back over. That way, we don't have water above the controls. Okay. No isolation flanges on these circulators, just standard flanges on there. And this one came in. This is PEX tubing wrapped around a vent connector coming off of a conventional boiler. So I kind of sarcastically said, is this some type of attempt at heat recovery? Not a good idea. PEX is great stuff, but I'm not sure if it's up to 300, 350 degree temperatures. Flue gas is going up through that pipe. And I look at this and I just wonder, how come this piping just didn't get extended? Maybe this is very close to the wall. I'm not sure, but I would certainly try to extend that piping over here and avoid that situation. Okay. All right. This is one of my favorites right here. We usually ask, what do you suppose this fellow is doing over here in the lower left? And the most popular answer has been he's praying. He's praying that he'll have inspiration to fix this assembly of various components. And this is what I call design as you solder. And you can see there's a lot of good hardware here. There's zone valves and circulators and motorized mixing valves, controls, and so forth. But to me, this looks like nobody really had a plan in mind, or certainly a plan on a piece of paper before they started putting this together. So it looks like it was done kind of 5 minutes at a time and so forth. So again, put yourself in a position where you're the technician walking in and it's midnight and it's a no heat call and it's below zero outside and you're trying to figure out what in the world is this and where do I get started? I'm not sure how this thing is supposed to work, even when it's working correctly. Anyway, it's probably not going to make one of the award ceremonies in the industry for professional installation quality. So spend some time, think about a mechanical room layout. Today, there's all kinds of software that you can do. If you don't want to do software, get yourself a piece of graph paper and lay out your mechanical room. You're laying out several $1,000s worth of components. Think it through before you start getting out your tools to install it. This is a situation that I call this a thermally constipated attempt at floor heating. You're looking at the underside of a floor deck here, floor trusses, and somebody has tacked some 1/2-inch PEX tubing onto the lower chord of those trusses, thinking that this somehow is going to heat the floor up above it. And oftentimes in our industry, we'll read about quote unquote radiant tubing, as if this tubing has some kind of magical qualities to it. It's plastic pipe. It doesn't really radiate heat very well, and certainly the amount of surface area that we have is not enough to adequately heat that floor. I got this photo because the installer that went in to correct this had to basically take this all apart and redo it. So don't do that, okay? Remember the term thermally constipated. And this, by the way, this also applies to tacking the tubing without aluminum plates up to the bottom of the subfloor. I don't like that. It's very limited in what it can do from a heat output standpoint. And you'll tend to create what's called striping. You're going to get hot areas on the floor directly above the tubing. And when you get that first call that the room isn't heating properly, you go back, you turn up the water temperature, that's just going to make that striping situation worse. Eventually you could discolor the floor. We've seen vinyl flooring discolored because of high temperatures in the PEX tubing, where the tubing's just been stapled up to the bottom of the subfloor. You don't see this in other parts of the world, by the way, only in North America. We call it plateless staple up. It's not a good idea. There it is. There's plateless staple up, one tube in a 16-inch on-center joist cavity. Hopefully they're going to put some insulation. Take a look at the tubing over here. You'll see a big air gap. Very, very inadequate as far as heat output. Okay, take a look at this one. Again, not exactly a showcase system in terms of level and plumb or use of proper fittings. There's a couple things here. One is that circulator is extremely close to that mixing valve. And I'm assuming here that we're coming out of the mixing valve here and going up. We're going to have turbulence coming into that circulator. And again, we'd like to see 10 to 12 pipe diameters of straight pipe on the inlet side of a circulator so we don't create that potential for noise in the circulator due to turbulence. The other thing is wrong, mixing valve without an actuator. This is like a car without a steering wheel. You cannot set that valve at some location where it's always going to provide the right temperature. It might for a moment, given a certain flow rate of hot water and return water and a certain temperature of hot water and return water, but the minute you change any of those four, you change either flow rate or either temperature, that valve can't react to that change. And the water temperature going out of the valve is going to, it's not going to be where you want it. So if you're going to put in a mixing valve like this, it needs to have a motor and an actuator on it. We'd call this a dumb mixing valve. And I use that term simply to describe it. There's nothing wrong with that mixing valve as far as a quality component. It simply doesn't have a brain. All right. It doesn't have any device that can steer it where it needs to go as those temperatures and flow rates change. Okay. I'm not overly impressed with the wiring in this project, by the way. Here's another one. Same problem that we had before. This is actually on a large a church not far from where I live. I got a call to go up and take a look at this. And again, we got two mixing valves there. And I think what happened here is the contractor underestimated the price and said, well, I'll just leave the actuators and the motors off these mixing valves. And again, all kinds of flue gas condensation problems in the boiler and temperature control problems on the supply side of the circuits. It would be a simple fix for this valve, not so much on the back. Obviously, there's not enough room in there to get that actuator in there. They're going to have to repipe it, but that would be a way to fix this. Okay. I'd like to walk into this at midnight. All right, this is an $80,000 heating system. I'm sure many of you recognize these are temperature controls up here, set point controls that probably go up to some kind of sensors in different rooms up above. So instead of room thermostats, we're going to have temperature sensors, and then we're going to adjust temperatures down here. But we've got a real mess of wiring. We've got low temperature wiring, we've got line voltage wiring, covers off, and so forth. Hopefully there's a schematic. I have my doubts as to whether that is the case or not, but it's just a very poor organization of wiring. Again, spend some time, think about how you want to organize it. Maybe use some wire gutter for both, a wire gutter for line voltage as well as a separate wire gutter for low voltage would clean that up quite a bit. You're going to see more photos of this in just a minute. There it is. I just moved the camera over about 3 feet. A number of things going on over here. We've got 8 circulators. You can't see them all. There's actually 4 here, and then here's 5, 6, and trust me, 7 and 8 are out there. And if we follow the headers back, it comes down, it comes into these T's here, the 2 headers, and it drops down, it comes back up, and it goes into this right here. And here we have a CV of probably 3 on this thermostatic valve. So we've got 8 zone circulators. This is a large house. I would guess this is maybe 5 to 6,000 square feet. So we've got 8 circulators trying to draw through a single 1-inch line-sized thermostatic valve, and very, very high flow restriction in that valve. And it gets better, okay? Here's a swing check on a vertical pipe. Not a good idea, whether the flow is going up or down. If it's going down, which I think, well, it's hard to say there. I think it is going down through that valve. That flapper is just going to hang open. If you put it the other way, what can happen is the flapper can slam shut, and that'll give you a very pronounced water hammer. So don't use swing check valves in vertical pipe. Use a spring-loaded check valve there. This is what I call a pump Band-Aid. It looks like the installer had a circulator here, but second guessed themselves and removed it and put some pipe nipples and couplings and flanges to patch up that. I'm not impressed by that. And then here's one of my other pet peeves. When you're soldering next to wood, whether it's plywood or floor joist, get a solder pad or a piece of metal or something, and don't scorch the wood. You know, the homeowner comes back and looks at this and says, my gosh, this installer almost burnt down my house today. That's just very unprofessional to do that. So you see a variety of problems with this right here, both sloppy wiring and kind of poorly organized piping here. This was a project not too far from me. And some of you will recognize this is a standard high limit control on an oil-fired boiler. And those that do recognize this know that anything that connects between the TT terminals will enable that burner to operate. And a copper wire will do that really well, 24/7, 365 days a year. And this was in a town municipal building with floor heating. And actually, it was the one where the vent connector was completely corroded through as well. But we found out something a little later on. It was kind of interesting twist here. The installing contractor also sold fuel oil. So this ensures that they're going to sell the maximum amount of fuel oil. I was on this project, I believe it was a day in June, and the boiler's firing off on limit. Absolutely no call for heat in the building. The boiler's just sitting there between maybe 160 and 180, just waiting to, you know, fire up to 180, wait for the jacket to dissipate enough heat, fire up the boiler again, and so forth. At the same time, the air conditioners are trying to run. So don't jumper out the TT terminals and leave that as, you know, you can do that as a temporary thing if you're just trying to test something, but obviously leaving it that way is not good. So where was this guy during wiring codes class? We've got quite a mix of wiring in here. Hopefully this is low voltage, hopefully. But there is an answer to that. And the guy skipped the wiring codes class and he went to pipe sculpture class. And I know at least one person looking at this webinar recognized this. I thought this was very creative. We've got some pump flutes here, a couple nice, I think B&G 100s down at the bottom for anchors, and a nice expansion tank up there for a head. So got to do something when you're bored, I guess, right? How about this one? Here's a couple boilers, and this all the information I have about this system is this photograph. And I'm sure most of you are drawn, your attention is drawn to this rusty stain over here on these on this wall. And what's going on here? Is a pipe leaking? And I think what's happening here is these boilers are operating with flue gas condensation, at least this one. And I think up above here, if you follow these flues up, my guess is there's a hole in the vent pipe, and the condensate is coming down, and it's probably hitting this pipe, and it's just spattering. Some of it's going back on the wall, some of it's going onto the top of the boiler. But certainly there's something wrong there, and my guess is that is flue gas condensation. And I also look at high limit. Well, these are not manual reset high limits. These are standard strap-on aquastats, and my question is, what are they doing? You know, maybe there's a legitimate function. I honestly don't know, because we do have limit controls on the boiler down here. You know, if this is intended as a secondary high limit, it doesn't meet code because it's not a manual reset. It doesn't have the little button in the front that you'd be pressing to reset it. And then finally, some situations just defy description here. And I also like to put this up with a live audience. There's a lot of funky things going on here. I think probably one of the best is how the expansion tank is being supported here with a couple pipe hangers, some 12-2 Romex, some kind of a Boy Scout knot down here. Over here, we've got circulators mounted at compound angles. We've got some galvanized pipe, and we certainly have plenty of half-inch PEX. Some of it stapled to the floor or clipped up to the floor. Some of it just waiting for somebody to walk by and catch their neck on it, I guess. And by the way, this is not a boiler. This is a tankless water heater. This is what happens with do-it-yourself, get it from the internet, anything goes type installation. And I think that is it. So I know it is 2:30. Bob, do we have time for a few questions?
I think the team's been pretty much covering them, but if Cody or Kevin or somebody has one that they want to throw out there, we'd be glad to entertain. And some of them pretend to the slides that you're on as you went through them, so it might be a little tricky to remember what's what. But certainly we'll get to anybody that submitted a question either before the presentation or during the presentation. We'll make sure that we get back to you. We'll send you an email and answer the question if it didn't get answered throughout the presentation. But yeah, that was a lot of, again, information, and even 90 minutes isn't enough time to go through this adequately. But I think you hit a lot of, the touching points for what we see out there, obviously, and the corrections for it.
Yeah, so. And again, Hydronics number 19, folks, if you want more details, several of those error situations are covered in more detail in Hydronics number 19, which again, just go to the Caleffi website under the link for Hydronics, and you can download the PDF on that.
Yeah, I was going to say, John, we had a number of questions in here about piping parallel like indirect tanks and domestic hot water storage tanks. I think that's probably a little too complex for kind of the end of the webinar here, but some great questions that came in. I tried to keep up with them the best I could, and I'm sure we'll get back to you as time allows here in the future. But there was a lot of great questions, a lot of great information, John. We really appreciate it for sure.
Yeah, it's it's interesting to go back. I think in terms of training people, one of the things I found over the years, oftentimes when you show somebody what not to do, you actually get better attention than if you're describing just what to do. And I don't know if that's inherent fear of failure, but we found it's pretty effective to show what not to do. And the other thing that I'd stress is when you go back and look at these, again, think about fundamentals. Think about, for example, hydraulic separation. We looked at what does provide it, what doesn't provide it. Think about, point of no pressure change. Anytime you're putting an expansion tank in a system, look at where your pumps are, and remember, pump away from it. Differential pressure control with zone valve systems. Today, the variable speed pressure regulated circulators with any type of valve-based zoning it's pretty much I guess I'd call it the new normal, as opposed to fixed speed circulators and differential pressure bypass valves. So a lot of fundamentals are still embedded into these drawings.
If I had to take a guess, John, I think the reason why those pictures of those subpar installations are so effective is because they're just deathly afraid of actually having their installations in your presentation someday, and there for everybody to see. I noticed you weren't crediting any of those photos, and I was kind of wondering why.
Absolutely not. No names, no locations. But I will tell you this, over the years, we've had people call and they'll say, now, John, you have to realize in our part of the country, we don't have anybody that really knows what they're doing with hydronics. And hence my phone call. And what I found is that's true everywhere, whether it's the Northeast, the Pacific Northwest, everywhere. There's people that just seem to be uncomfortable with what they're able to find locally for people that they feel are competent. And this is again, it's not really that complicated if you think about these fundamentals. Go back again. I'll stress hydronics number 19. The reason we wanted to do that is because of this idea that people, when they start a hydronic system, you want to get away from the idea that you have to reinvent the wheel with every new system. Just go back to the fundamentals. If you're trying to create a primary, secondary system, make sure the T's are close together. Don't second guess it and say, if I just move all these T's around, I'll have the same supply temperature and so forth. Because typically, if you're breaking away from what one of the several proven system concepts that we talk about in Hydronics 19, you may think that you're improving it in one area, but you're probably overlooking something else that's going to happen that is going to work against you. So stick to the proven systems.
For sure. Anything to add there, Bob, then?
No, I think a job well done again. And yeah, sometimes it's nice to hear somebody talk through an issue of hydronics instead of just page through it. And that's, I think, what you brought to the game today, Sig, is that these are in hydronics issues that we've done in the past. It's just nice to hear the explanation a little bit. So.
Sounds good.
Yeah. Right. Any more housekeeping, or what do we got here?
Oh, yeah, we do have some more housekeeping slides here, don't we? Yes.
Yeah, that's our team up in Milwaukee, getting back to work in the office these days. So anytime you have a question on product application, troubleshooting, or whatever, don't hesitate to email us or call us, and we'll help you where we can. So thanks to the boys up in Milwaukee for that. We've got a podcast going on with Greg and Dan. They got some good information on different topics that they're doing a little podcast series on. They do a good job with that. Nice, friendly voice.
Yeah, my compliments to them too. I listened to one of these, and these two guys work together really well. So very,
yeah, that's
very
a
well
nice relationship as far as their voice and everything. So Cody's putting together this little series. It's a quick 5 minutes. If you have 5 minutes, what you need to know, and he's been producing those and talking through those. So we've got a lot of different places where you can get information if you need it or want it. And yeah, those other different places on social media that you'll find us. We try and get there every day and answer questions and help people out. So if you want to communicate with us in this format, we're out there. And
I think that's it.
Yeah, well, thanks everybody, and thanks to the team up in Milwaukee and the Siggy and everybody that's on the back end of putting these together. It takes a little bit of work to get all these compiled, but thanks everybody.
Thanks, John.
Thank you, guys.
Yeah,
Have a good afternoon.
And the next one, team.